Hello and welcome. This will be a study guide for Chapter 4. This project was put together by Carlos Fernandez, Max Woodbury, Dakota Rennemann, Zach Tsarnas, and myself, Douglas Easom. Starting off, we'll have Section 4.1, Divisibility and Modular Arithmetic. The definition of division is if there exist integers a, b, and c, where a is not equal to 0, and a divides b, then b equals a times c. The notations are as so. As you can see, this notates that a divides b, and this notates that a does not divide b. As you see below, 4 does not divide 9, but 4 does divide 8. The theorem is a, b, and c are integers where a is not equal to 0. If a divides b and a divides c, then a should divide b plus c. It being seen by the example, 4 does divide 20, so it's true. If a divides b and then a should divide b times c for all integers c. For the example, 4 into 8, 4 into 12, 4 does indeed go into 8 times 12. If a divides b and b divides c, then a should divide c. Again, in the example, it becomes true. Division algorithm. If a is an integer and d a positive integer, then there are unique integers q and r with 0 is less than or equal to r is less than d, which that a equals dq plus r. So you can see the variable definitions there. First example is find the quotient of the remainder of 89 into 9. The quotient of 89 is 8, and the remainder is 8 as well. Find the quotient of the remainder of 75 into 7. Quotient is 10, remainder is 5. And this is all using the same thing as we saw before. We'll probably go more into this. For section 4.2, it's integer representations and algorithms. We can use positive integer b greater than 1 as a base because of this. Let b be positive integer greater than 1. Then if n is a positive integer, it can be expressed uniquely in the form as seen here. A continuing is where k is a non-negative integer, a sub 0, a sub 1 through a sub k are non-negative integers less than b. And as seen here, these values are called base b digits of representation. The representation of n given in Theorem 1 is called the base b expansion of n, and is denoted by as follows. We usually omit the subscript 10 for base 10 expansions because it is so common that it doesn't need to be repeated or seen every single time, because decimal is so common. Most computer represents integers by base 2, which is also known as binary, using zeros and ones. The decimal expansion of the integer as below should be used in binary. So we want to write this in binary and convert it back to decimal base 10. So starting from the right, you get 0, 1, 2, 3, 4, 5, 6, 7, 8. So this should go up to power 8. And all you do is simply put the number that matches up whatever the power is, and then you add them all together. So as you can see, the 1 is in the 8 spot, so 1 times 2 to the 8th, and continue down the line, equals 351. Octal is basically the exact same, except it's base 8, so you'd be doing 8 to the powers instead of 2, and it's also only the numbers 0 through 7. So this value of 7016 base 8 comes out to be 3,598 using the same method, 0, 1, 2, 3, and it's 8 to the s powers. Hexadecimal is no different except for the fact that the values are from 0 to f, so it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but because base 10 only has room for 10, the last 5, 6 digits, A through F, have to be represented by letters. So 10 through 15 are letters instead. Again, though, it's base 16, so it's 16 to the powers. 2AEOB will come out to be 175,627, based off the same power of 0, 1, 2, 3, 4. Base conversion is to construct the base b expansion of integer n, divide n by b to obtain a quotient and a remainder, using the formula you see in here. The remainder of a sub 0 is the rightmost digit of the base b expansion of n. Next, divide q sub 0 by b, as seen here. The remainder of a sub 1 is the second digit from the right in the base b expansion of n. Continue by successively dividing the quotients by b, obtaining additional base b digits as the remainder. The process terminates when the quotient is 0. So as we can see here, 1, 2, 3, 4, 5, we want to convert this from base 10 to base 8. We can divide constantly by 8 until we get to the quotient of 0. The remainders of the digits, starting from the bottom, is the new base 8 number. So 30071. Continuing, we want to convert for octodecimal. It's very, very similar, except for the fact that you want to group into bases of 3. So as seen here, 0, 1, 1, when converted, ends up being 3. 1, 1, 1 ends up being 7. 0, 1, 0 ends up being 2. 1, 1, 1 ends up being 7 again, and 1, 0, 0 equals 4. So you just simply break it into those parts, and then you get your base 8. Almost exactly the same, except slightly different, is you just break it into bases, like groups of 4, to use it for base 16. So you get 3E, B, C. Those are each of those groups. Some interesting facts is that the binary system actually kind of originated in China near the 9th century BC, except theirs was based off of 3-bit and 6-bit binary numerals. So it was 8 trigrams and the 64 hexagrams, as you can see to the right. And it was seen almost as early as like the ancient China's, like the dynasties. So that's decently interesting. The octonumeral system is used in aviation, so transponders in aircraft will actually send a code down to the base. It will be like responded to, and the code can distinguish different aircraft based on the code they received, the number. Hexadecimal can be used in computers as they got bigger because of the fact that it was more convenient to group by 4 instead of 3. So they doubled the number of the symbols, which would represent the 16 values instead of the 8 or like the base 10. Instead of the 8, the hex means 8 and the decimal means 10, so it's referred to as hexadecimal. So these are some uncommon bases, but it's the same principle. Is if you want to convert two things, it's just going to be 0 and 1 times the base. So to get 4C, you do 13 to the first power times 4, and then 4 times 13 is 0. This is continued through all of these. And then also, it's like for the 25, it's the exact same thing. You just convert this into these, and then you just easily come out with this. It's the same as 25 to the first power based off of whatever's there. 25 to 0 based off whatever's there. Continue to section 4.3, it's primes and greatest common divisors. These numbers can be broken down into two groups of positive integers. One is prime, which basically means that the number can only be divided by itself in 1. And composite numbers, which means it can be divided by many different numbers. So like 4 can be divided by 4, 2, and 1. 12 is 12, 6, 4, 3, lots of things. The theorem is every positive integer greater than 1 can be written uniquely as a prime or product of 2 or more primes, where the prime factors are written in order of non-decreasing size. For our first example, we start with 872, and you can see we want to just divide down, divide down, divide down. We end up getting down to 109, which is a prime itself, so our prime factorization is 222109. Again, we see example 2, it factors out to 2255. There are actually an infinite many primes that exist. However, as you get higher and higher, it gets very, very hard to figure them out. As this is assuming, as is seen before, that the prime is either prime, like the number is either prime itself or that it is a base of primes. So it's a product of primes. So if it's like 4, then it has to be broken down into 2 and 2. But if it's 7, 7 is already prime, so it's got to be one of those two. So consequently, there are infinitely many primes to be found. However, one thing that's not commonly well known is that there is no formula to find large prime numbers. So it's very, very hard to get super, super, super large prime numbers. So there's not a formula. A modern day example is the RSA encryption, which is basically somebody taking 2 prime numbers or more and having it as like a public key or like a password per se. And basically anybody that wants to contact them would have to know these prime numbers and know how to use them in order to contact them. The bigger the prime number, the more combinations there are to create the key, and it's really, really hard to find. Like no normal passerby will just be able to decode it without thinking about it, without incredibly long time. Some conjectures about them is the gold box conjecture, saying that every integer n, as long as n is greater than 2, is the sum of 2 primes. It has been verified by computer for all positive even integers up to 1.86 times 10 to the 18th. The conjecture is believed to be true by most mathematicians. Continuing, the twin prime conjecture is that there are infinitely many twin primes. This is being said as 3 and 5, 5 and 7, 11 and 13, etc. And it just infinitely keeps going. The largest one found has 388,342 decimal digits. It's a number that I can't even begin to comprehend. They're very, very large. Continuing to least common multiple, it is a reverse of greatest common divisor. starting with letting a be positive integers. C is the least common multiple if and only if a is divisible by c and b is divisible by c. And there's no smaller number satisfies this, basically saying that least common multiple of a, b equals c. So to be able to do this by just listing out factors, it's very easy. 10 times 1 times 2 times 3 times 4, it is the first number that appears in both columns. But this can be very, very tedious. If you're trying to look for a much larger number, or much odder numbers than just 10 and 30, it just can take forever. So there's a better method, which is the Euclidean algorithm. Efficient method to find the GCD of two integers is basically that if GCD of AB equals the GCD of AC, if A and B is greater than B and C is the remainder when A is divided by B. Using this formula, you can see here that it's very, very common to the DQ plus R that we saw earlier, except now it's using the previous remainder. So it's basically move down to 111, move down to 90, divide again into it, move down, move down. As soon as you hit 0, the previous remainder is what your greatest common divisor is. So in this case, 111 and 201 is 3. Bezout's theorem is to take A and B as positive integers and the exist integers S and T such that GCD of AB equals SA plus TB. This is called linear combination. It's basically saying that there's coefficients that would match that. Using Euclidean's algorithm backwards, you can find the GCD as a linear combination. Write the equation in terms of remainders, then substitute each remainder of the previous question. So in this exercise, we'll be doing 21 and 44. First, we start and find the greatest common divisor. As you can see here, we do the same process. We end up with 0, so 1 is our greatest common divisor. Just continuing, is we want to put this into two equations. We find here that's this 2 equals 44 minus 21 times 2, and we get 1 equals 21 times 2 times 10. We substitute 1 into the second equation. Continuing, we combine the terms, and this ends up being 1 equals 21 times 21 plus negative 10 times 44. And that is your final S and T values that you could possibly get. This has been a study guide / review for Chapter 4. I hope you enjoyed and I hope it helped, and I'll see you later.